Hey guys, it's Lainey, and today I'll be presenting a forensic evaluation of the catastrophic failure and remediation of the reinforced soil slope, often called the RSS, at Yeager Airport International in West Virginia. This case is significant not only because of the scale of the structure, but also because of the lessons it offers for geotechnical engineering practice and public safety. Yeager Airport, located in Charleston, West Virginia, required a major runway extension to meet FAA safety standards. To achieve this, engineers designed a near-vertical reinforced soil slope using geogrid reinforcement, making it the largest of its kind at the time. The slope's steep geometry and challenging local geology demanded innovative solutions, with fill material sourced locally and the structure built to blend with the natural terrain. Despite these efforts, the project faced significant risks. 6 years after construction, distress indicators such as tension cracks and settlement began to appear. In March 2015, these warning signs culminated in a catastrophic slope failure, which blocked a creek, damaged nearby properties, and disrupted airport operations. In this presentation, I'll guide you through the underlying causes of the failure, the forensic evidence uncovered, and the engineering solutions proposed to prevent similar incidents in the future. We'll also discuss the broader lessons for geotechnical engineering and professional responsibility. A detailed forensic investigation revealed several critical deficiencies in both the design and construction of the slope. First, the subsurface exploration conducted before construction failed to identify weak shale clay-stone layers beneath the reinforced soil slope. These layers are prone to strength reduction over time and were neither considered in the design nor removed during construction, leaving the slope vulnerable to instability. Additionally, the reinforced soil slope was founded on compacted soil rather than freshly excavated bedrock, and the rock face was not benched. Without benches throughout the reinforced soil slope, stormwater runoff will reach higher velocities and in turn erode the soil faster. During construction, the lengths of the geogrid reinforcement were also shortened from the original design specification, and laboratory testing showed that their tensile strength had been reduced due to installation damage and creep. But the most critical thing is the design did not include any drainage provisions, allowing groundwater to accumulate and further weaken the soil-to-rock interface. The failure mechanism was compound and developed progressively. Groundwater infiltration and sustained stresses caused the shear strength along the shale claystone interface to decrease from its peak value to a fully softened state. As the interface weakened, shear deformations transferred additional stress to the geogrid reinforcement, which responded with increased strain and creep. Eventually, the geogrids ruptured, and the failure surface propagated beneath and through the reinforced zone. This event highlighted the importance of considering three-dimensional effects in slope design, as traditional two-dimensional methods may overestimate stability by neglecting side resistance and the orientation of reinforcement relative to the direction of movement. Multiple engineering teams investigated the failure, and while their interpretations varied, a consensus emerged around several key contributing factors. Some experts attributed the collapse to primarily insufficient geogrid length and strength, noting that the shortened reinforcement in the lower slope was unable to provide adequate resistance. Others emphasized the role of groundwater infiltration and the long-term reduction in shear strength at the soil-to-rock interface. The most credible analyses recognized the interplay between these factors, highlighting the combined impact of inadequate subsurface investigation, poor foundation preparation, and suboptimal geogrid design. Although some experts suggested that raising the factor of safety could have prevented the collapse, I believe that true design resilience depends more on thorough subsurface investigation and effective draining planning than on simply increasing safety margins. In typical conditions, a reinforced soil slope with multiple benches would be a practical and cost-effective solution. Benching improves surface drainage, slows runoff velocity, and enhances overall stability. However, the conditions at Yeager Airport are far from typical. The presence of extensive weak shale claystone layers and uncertainties in long-term shear strength and groundwater behavior introduce a high risk of deep-seated failure that a benched RSS alone may not adequately address. For this reason, I recommend a hybrid solution, a combination of a benched reinforced soil slope and an anchored retaining wall. The benches would manage surface water and reduce erosion, while the retaining wall would provide deep structural support anchored into competent sandstone. High-strength tendons drilled into the underlying rock, also known as tiebacks, would actively resist lateral earth pressures and transfer load into stable bedrock. This dual approach creates redundancy and stabilization, addresses both surface and subsurface failure mechanisms, and ensures a higher factor of safety for critical infrastructure. Professional responsibility is essential because the decisions made by engineers directly impacts public safety and trust. By upholding ethical standards and conducting rigorous evaluations, we contribute to the well-being of communities and reinforce the integrity of our profession. Throughout this evaluation, my professional responsibilities included minimizing any uncertainty and bias by distinguishing between facts, assumptions, and opinions. Uncertainty was managed by triangulating multiple sources of evidence, including field observations, laboratory testing, and advanced analyses. Where data gaps existed, assumptions were clearly stated and treated with caution, ensuring that conclusions were based on the best available information. Bias was minimized by systematically evaluating competing interpretations, documenting the rationale for accepting or rejecting each, and grounding recommendations in measurable factors such as pore pressure, reinforcement length, and observed settlement trends. This approach upholds the highest standards of professional responsibility, ensuring that recommendations are defensible, transparent, and aligned with the duty of care expected in geotechnical engineering practice. The catastrophic failure of the reinforced soil slope at Yeager Airport underscores the critical importance of thorough geotechnical investigation, robust design, and diligent construction practices for large infrastructure projects. Forensic analysis revealed that a combination of insufficient subsurface exploration, inadequate foundation preparation, shortened geogrid reinforcement lengths, and long-term reduction in soil-to-rock interface strength contributed to the collapse. Moving forward, the recommended approach is to implement a hybrid solution that combines a benched reinforced soil slope with an anchored retaining wall, supported by comprehensive subsurface investigation, proper foundation preparation, and effective drainage systems. Ultimately, the lessons learned from Yeager Airport's experience highlights the necessity of integrating sound engineering principles, proactive risk management, and continuous monitoring to ensure the safety and longevity of critical infrastructure. References for this presentation include published case histories, lectures, engineering analyses, and industry guidelines. Thank you for watching as I discussed my findings on the Yeager Airport reinforced soil slope failure. I appreciate the opportunity to share these findings and discuss the lessons learned. Happy holidays!